How Earth Moves, a simple title, yet behind it lies one of the quietest, most astonishing truths in the universe. Most of us spend our entire lives believing we are still. Feet on the floor, breath soft and steady, a world that feels unmoving beneath us. But tonight, as you settle in, something gentle begins to unfold. The ground under you is spinning faster than the speed of sound. The entire planet is gliding around the sun in a silent arc of light. And all of us, every ocean, every mountain, every moment, are drifting through the galaxy together, carried by motions we never feel. This is the hidden dance of our world. A dance written in cycles, tilts, shadows, and ancient rhythms that shape every sunrise you've ever seen. So let your breath slow. Let the night open a little wider, and allow the calm pull of the cosmos to guide you inward. Because once you see how Earth truly moves, stillness begins to mean something entirely different. Before we begin, if this gentle journey brings you a moment of calm, a soft like or a quiet tap on subscribe helps this little channel shine a bit brighter in the night. And now, let the night carry you deeper into the story. Welcome to Sleepy Science Stories. Part 1. The sun does not move. The earth spins. Every single second that passes, right now as you listen to these words, beneath the ground you stand upon, beneath the chair you sit in, beneath the bed where you rest, the earth is turning. It is rotating on its axis at a speed that would terrify you if you could somehow feel it. It carries you eastward, always eastward, faster than the speed of sound, faster than any commercial aircraft, faster than most things you will ever experience in your ordinary life. And yet you feel nothing, not the slightest sensation of motion, not the faintest hint that you are hurtling through space. You do not feel it because everything around you moves in perfect synchronization. Your body, the air molecules surrounding you, the walls of your room, the trees outside your window, the soil beneath the pavement, all of it, every atom within hundreds of kilometers of your position, moves together at exactly the same velocity. There is no wind of motion because the atmosphere itself spins with the surface. There is no sense of acceleration because the rotation is constant. It never speeds up, it never slows down. It simply continues, second after second, hour after hour, century after century. Every wall around you, every structure humanity has ever built, every city that stretches across continents from New York to Tokyo to Mumbai, every ocean covering 2/3 of the planet's surface with water kilometers deep, all of it is spinning through the vacuum of space at 1,670 kilometers per hour around the planet's rotational axis. This axis is an imaginary line that runs through Earth from the North Pole to the South Pole, the line around which everything rotates like a cosmic wheel. And while that rotation continues without pause, without rest, without the slightest interruption, the entire Earth, this sphere measuring nearly 40,000 kilometers in circumference, is simultaneously racing around the sun at nearly 108,000 kilometers per hour. This is your orbital velocity, the speed at which the whole planet travels through its elliptical path, chasing the same course it has followed since the solar system formed from a cloud of dust and gas more than 4.5 billion years ago. Think carefully about what this means. At this very moment, even as you sit perfectly still in your chair, even as you lie motionless in your bed, even as you remain completely stationary relative to your immediate surroundings, you are actually moving tens of thousands of kilometers every single hour through the fabric of space-time itself. Through space, through time, through the vast cosmic arena that stretches beyond comprehension in every direction. And yet, impossibly, it feels like nothing at all, like absolute stillness, like perfect, serene peace. That illusion, that extraordinary sensation of stillness amid such tremendous motion, is one of the most profound and beautiful facts in all of physics. It reveals something fundamental about how the universe operates on the deepest level, about how forces balance one another, about how objects move together through four-dimensional space-time without any awareness of their motion. It explains why ancient peoples believed Earth stood motionless at the center of creation while the heavens wheeled overhead. The illusion is perfect, convincing, total. It is also the quiet reason, the hidden explanation, for why the sun seems to rise in the east each morning and set in the west each evening. Though in truth, in physical reality, the sun never moves relative to us at all. It remains essentially fixed in space, sitting at the gravitational center of the solar system, while we orbit around it. Each dawn, each morning, light spreading golden across the land, is not the sun returning to us from some journey through the night. It is our own world, our own blue planet, gently turning back toward that star, rotating eastward, spinning once more to face the furnace that gives us life, that provides the energy for every ecosystem, every plant, every creature that has ever lived on this world. Earth completes one full rotation, one complete spin on its axis, every 23 hours, 56 minutes and 4 seconds. Not quite 24 hours, not the number you might expect. Astronomers have a special name for this precise measurement, this exact duration of one complete rotation. They call it a sidereal day, a term derived from the Latin word sidereus, meaning related to the stars. It represents exactly how long it takes for our planet to complete one full 360-degree spin relative to the distant stars, those points of light scattered across the night sky, so far away that they appear motionless, fixed in their positions like diamonds scattered on black velvet. The 24-hour day we live by, the one that structures our schedules and divides our time into manageable chunks, the one that determines when we work and when we sleep and when we eat our meals, is actually slightly longer than this sidereal day. The reason for this discrepancy is both elegant and profound, a consequence of the fact that Earth does not simply spin in isolation. While the Earth rotates on its axis, it also travels along its orbit around the Sun. Each day, our planet moves approximately 2.5 million kilometers through its orbital path, a distance so vast it defies intuition. Because of this orbital motion around the Sun, Earth must turn just a little bit more each day, just a few extra degrees beyond one complete rotation, for the same place on the surface to face the Sun again, for the Sun to return to the same position in your local sky. That additional rotation, that extra angular distance the planet must turn to compensate for its motion through orbit, takes approximately 4 minutes. 4 precious minutes that separate the sidereal day from the solar day. That tiny difference, just 4 minutes out of an entire day, just one part in 360 of a full rotation, reshapes the entire sky every single night. Over the course of 1 month, those 4 minutes accumulate into 2 full hours of cumulative shift. Over the course of 1 year, they add up to an entire day, a complete rotation that goes completely unnoticed in our daily lives, but fundamentally, dramatically changes the positions of stars above us, transforms the constellations we see at midnight, and alters the entire appearance of the night sky. So, the stars that gleam above you tonight, those ancient lights that have travelled for years or decades or centuries or even millennia to reach your eyes, photons that began their journey when dinosaurs walked the earth, or when humans had not yet evolved, or when civilizations you have never heard of, built monuments that no longer exist, are not in the same positions they occupied last season. They have shifted across the dome of the sky, not because the universe itself moved, not because those distant suns physically changed their positions relative to one another, but because you did. Because this planet beneath you travelled millions upon millions of kilometres through its orbit around the Sun, carrying you to an entirely new vantage point in space, a different perspective from which to view the cosmos. Our ancestors noticed this long before satellites, long before atomic clocks, long before telescopes, long before we could measure time to the nanosecond or position to the centimetre. They watched with patient eyes the changing length of shadows as seasons progressed from spring to summer to autumn to winter and back again. They recorded with careful notation the drifting constellations, marking which stars rose at sunset and which vanished below the horizon at dawn, which patterns dominated the winter sky and which belonged to summer. They built their entire civilizations around these observations, scheduling planting and harvest, predicting floods and droughts, navigating across trackless oceans using only the stars as guides. The Egyptians, those ancient masters of astronomy and mathematics and architecture, built their temples and pyramids with such extraordinary precision that sunlight would strike a single specific point, a particular stone or altar or chamber, only once each year. A cosmic alignment encoded into massive blocks of limestone and granite, monuments that have survived millennia. These structures were not merely buildings, they were calendars, clocks, astronomical instruments carved in stone. They tracked the motion of Earth through space using nothing but shadow and light. Today, thousands of years later, NASA confirms those same rhythms using technology our ancestors could never have dreamed of or imagined. Very long baseline interferometry, a technique so precise, so extraordinarily accurate, that it can measure the wobble and rotation of our planet to within fractions of a millisecond. Scientists compare radio signals from distant quasars, those incomprehensibly bright objects powered by supermassive black holes billions of light years away, using them as reference points so stable, so utterly fixed in their positions that they serve as perfect cosmic markers, lighthouses scattered across the universe. By tracking these signals simultaneously from multiple locations on Earth, from radio telescopes separated by thousands of kilometers, researchers can determine with absolute precision exactly how fast the planet is spinning at any given moment. They can detect the tiniest variations, the smallest wobbles, changes that would have been impossible to measure just decades ago. This is how we know, with certainty, that Earth's rotation varies slightly from day to day, influenced by forces both on the surface and deep within the planet. And here is something remarkable, something that reveals just how dynamic our world truly is. This rotation, this spin that seems so constant and unchanging, so utterly reliable that we build our entire concept of time around it, is not actually perfectly uniform. It varies, subtly but measurably. When massive wind patterns shift across the globe, redistributing billions of tons of air from one latitude to another, the rotation rate changes ever so slightly. When enormous ocean currents change direction or intensity, moving vast quantities of water across thousands of kilometers, the rotation adjusts. When glaciers melt at the poles and redistribute water toward the equator, when ice sheets collapse and flow into the sea, each of these events moves mass on a rotating body, and whenever mass moves on a rotating body, the rotation itself must change to conserve angular momentum. It is the same principle you can observe when a figure skater spins. When they pull their arms inward toward their body, they spin faster, sometimes dizzyingly fast. When they extend their arms outward again, they slow down. This happens because angular momentum, the product of rotational speed and the distribution of mass, must be conserved in the absence of external forces. When mass moves closer to the axis of rotation, the rotation speeds up. When mass moves farther from the axis, rotation slows down. Earth follows this same law. When mass shifts toward the equator, away from the poles, Earth's rotation slows imperceptibly. When mass concentrates toward the poles, rotation speeds up slightly. After large earthquakes, particularly the most powerful ones that shift billions of tons of rock deep beneath the surface, sometimes moving entire tectonic plates by meters in a matter of seconds, NASA's Jet Propulsion Laboratory in Pasadena, California, has observed measurable changes in the planet's rotation period. Sometimes these changes last only a few microseconds, millionths of a second, barely detectable even with atomic clocks. But they are absolutely real, they are physically measurable. The devastating earthquake that struck Japan in 2011, magnitude 9 on the Richter scale, actually shortened the length of Earth's day by approximately 1.8 microseconds by redistributing mass and changing the planet's moment of inertia. These measurements remind us, gently but insistently, that this world we live on is not a perfect, unchanging sphere of rock spinning in a vacuum. It is dynamic. It breathes like a living thing. It adjusts constantly to forces within and without. The atmosphere circulates, the oceans flow. The continents drift slowly across the surface. The core churns with liquid metal. All of this creates a planet that is constantly responding, constantly changing, constantly adjusting its motion in tiny ways we can now detect and measure. That precision, that remarkable stability, even amid these tiny natural variations, is precisely what makes life possible on this world. The rotation balances temperature across the globe, ensuring that no region remains in darkness too long or bakes under sunlight without relief. It prevents one side of the planet from becoming an oven, heated to hundreds of degrees, while the other freezes into permanent darkness at temperatures hundreds of degrees below zero. Without rotation, without this constant turning, temperature extremes would make Earth utterly uninhabitable for anything we would recognize as life. The rotation also drives the jet streams, those rivers of air flowing 5 to 10 kilometers above the surface at speeds that sometimes exceed 300 kilometers per hour. These high-altitude winds determine weather patterns across entire continents. They carry moisture from the oceans to the land. They distribute heat from the equator toward the poles. They create the storms and fair weather that shape ecosystems and agriculture. Without Earth's rotation, the jet streams would not exist, and weather would be completely different, perhaps impossibly chaotic. The rotation shapes the global cycle of daylight and darkness that defines every ecosystem, every biological rhythm, from the smallest bacterium that can barely be seen under a microscope to the largest whale weighing 100 tons swimming through the ocean depths. Circadian rhythms, those internal biological clocks that tell organisms when to wake and when to sleep, when to feed and when to rest, evolved over billions of years in response to the reliable pattern of day and night created by Earth's rotation. These rhythms are encoded in the DNA of nearly every living thing on the planet. Without this rotation, our world would be utterly, completely unrecognizable. One hemisphere would bake under endless, unrelenting sunlight, its surface scorched to temperatures that would melt lead, its atmosphere boiled away into space. The other hemisphere would freeze in eternal night, colder than the coldest reaches of Antarctica, its air condensed into liquid and then solid on the ground. Atmospheric circulation, that delicate balance of pressure and temperature that creates weather, would collapse entirely. Oceans would boil on the sunlit side and freeze solid, kilometers deep on the dark side. Life, as we understand it, as it has evolved over billions of years, could not possibly exist under such conditions. Carl Sagan, that poet of the cosmos, that gentle voice who brought wonder to millions, once observed with characteristic elegance, "The Earth is a very small stage in a vast cosmic arena." He was absolutely right, of course. From the perspective of the universe, Earth is insignificant, a mote of dust, a pale blue dot barely visible from the edge of our own solar system, utterly invisible from any other star. But it is also a stage in constant, ceaseless motion, endlessly spinning under invisible laws of angular momentum that link us to every rotating body in the universe, from the smallest particles to the largest structures. From the tiniest electrons orbiting atomic nuclei at speeds approaching the speed of light, to neutron stars spinning hundreds of times per second, to the grandest spiral galaxies wheeling through intergalactic space over hundreds of millions of years, spin is one of the most universal patterns in nature. It is one of the fundamental ways the cosmos organizes itself, one of the deepest symmetries woven into the fabric of reality. Rotation is everywhere, in every atom, in every planet, in every star, in every galaxy. It is as fundamental to the universe as gravity itself. Think carefully about this profound fact for just a moment. At this exact instant, as you read these words or listen to this voice, your body, every cell within it, the air surrounding you, the chair beneath you, the floor supporting that chair, the ground beneath the building, even the individual atoms that make up your bones and blood and brain are all moving with exactly the same velocity vector, the same speed, the same direction, eastward, always eastward, and more than 1,600 kilometers per hour, depending on your exact latitude. That is precisely, fundamentally, why you do not feel the motion. Everything that matters to you, everything in your immediate environment, everything you can touch or see or interact with moves in absolutely perfect unison. There is no relative motion between you and your surroundings. It is a flawless synchronization that extends for thousands of kilometers in every direction. The most elegant example of inertia, of Newton's first law, ever experienced by conscious beings. You move, but you move together with everything around you, and so the motion becomes invisible, undetectable, utterly imperceptible. If the Earth were to stop spinning suddenly, even for just a single second, even for one brief moment before resuming its rotation, the consequences would be catastrophic beyond human imagination. They would be apocalyptic. Everything not firmly anchored to the bedrock of the crust, not bolted down to solid stone deep beneath the surface, would continue eastward at over 1,600 kilometers per hour. The atmosphere itself, all the air we breathe, would continue moving at that tremendous speed, creating winds of such unimaginable violence that they would scour the surface clean of everything that exists. Trees, buildings, mountains, all would be ripped apart by forces measured in megatons. Oceans, no longer held in place by the rotating frame of reference, would surge across continents in walls of water many kilometers high, traveling at supersonic speeds. These tsunami would dwarf anything in recorded history. They would sweep across entire countries in minutes, carrying billions of tons of water inland, drowning everything in their path. The kinetic energy stored in the moving water alone would be enough to destroy every city, every structure, every artifact of human civilization. Buildings and structures would be ripped from their foundations as if made of paper. Even mountains would crumble under the sudden shift of forces. Tectonic plates would buckle and fracture. Volcanoes would erupt simultaneously across the globe. Earthquakes of unimaginable magnitude would shatter the crust. The planet's delicate equilibrium, that precise balance of forces maintained over billions of years through the interplay of gravity and rotation and internal heat, would collapse in an instant. The world would become uninhabitable, a dead sphere of rock like Mars or the Moon. This is a purely theoretical scenario, of course. The laws of physics make such a sudden stop completely impossible. There is no force in the solar system, nothing short of an impact with another planet-sized object that could halt Earth's rotation instantaneously. And such an impact would not merely stop the rotation, it would destroy the planet entirely, vaporizing the crust and possibly fragmenting the entire world into countless pieces that would eventually recoalesce into a new planet or scatter into separate orbits. But geophysicists and planetary scientists study these extreme thought experiments nonetheless, because they help us understand how rotational energy shapes the stability of worlds, both our own Earth and the thousands of distant exoplanets we have discovered orbiting other stars across the galaxy. These studies reveal that the kinetic energy stored in Earth's rotation is almost incomprehensibly vast. If you could somehow convert all of that rotational energy into electrical power, it would supply humanity's entire energy needs for billions of years. The Earth is essentially a gigantic flywheel, storing energy in its motion, and that energy helps stabilize everything from the magnetic field generated in the liquid iron core to the climate patterns that make life possible on the surface. Through the remarkable data collected by the Gaia mission, a European Space Agency satellite launched in 2013 that has measured the positions, distances and motions of over 1 billion stars with unprecedented precision, astronomers have also made another fascinating discovery about our planet's motion. Earth's axis does not remain perfectly fixed in space, pointing eternally at the same spot. Instead, it wobbles slowly over time, tracing out a circle in the sky, a phenomenon known as axial precession. This wobble is caused primarily by the gravitational influence of the Sun and Moon pulling on Earth's equatorial bulge, that slight thickening around the middle created by the planet's rotation. This precession completes one full cycle every 26,000 years, a vast span of time that encompasses the entire history of human civilization multiple times over, and then some. 5,000 years ago, when the Great Pyramids were being built in Egypt, when the first cities were rising in Mesopotamia, Earth's North Pole pointed toward a completely different star than it does today. Right now, in our time, Earth's North Pole points very close to a star we call Polaris, which we know as the North Star. Polaris sits almost directly above the North Pole, barely moving as Earth rotates, serving as a fixed point around which all other stars appear to wheel. But this was not always the case, and it will not always remain so. 5,000 years ago, in the time of the ancient Egyptians, the pole pointed toward a different star entirely, one called Thuban in the constellation Draco the Dragon. Thuban served as their North Star, their celestial marker, the star by which they navigated and oriented their temples. The Egyptians even aligned some of their pyramids and structures to Thuban, encoding that alignment in stone. And 13,000 years from now, when our distant descendants look up at the night sky, assuming humanity still exists, the pole will point closer to the bright star Vega in the constellation Lyra the Harp. Vega will serve as the North Star for future generations, who will look back at our time and marvel that we navigated by a completely different star. The sky itself changes, not quickly enough for any human to notice during a lifetime, but inexorably across the centuries. Even our definition of north, something we think of as absolute and unchanging, an eternal direction fixed forever in the cosmos, is actually temporary. It is a moment in time, a snapshot of Earth's current orientation that will shift and change across the centuries and millennia. Everything we take as fixed in the universe, direction, daylight, the very idea of a day itself, is actually the result of motion, layered upon motion, complex interactions of physics occurring simultaneously at different timescales. Rotation combines with orbit. Orbit combines with precession. Precession combines with other, even slower wobbles and variations. All happening at once, all interwoven into a complex dance of physics and time that only reveals itself when we step back and look at scales larger than human lifetimes. And yet, inside all that staggering complexity, inside all those layers of motion and change and variation, there is something deeply, profoundly soothing, something almost spiritual in its reliability. Because despite all this movement, despite spinning through space at tremendous speeds while wobbling and orbiting and traversing the galaxy at nearly 800,000 kilometers per hour as part of the solar system's motion through the Milky Way, Earth remains stable enough for us to live, to breathe, to sleep peacefully beneath the stars without fear that the ground will suddenly lurch or the air will be ripped away or the day will fail to arrive tomorrow morning. The same physics that propels us through space, at speeds that beggar comprehension, also shelters us in balance. The same forces that could tear a world apart instead hold ours together in harmony, in equilibrium, in a state so stable that life has flourished here for billions of years. It is remarkable, extraordinary, perhaps even miraculous in the original sense of that word, something that fills us with wonder. So when you wake to gentle light tomorrow morning, when you see the sun appearing to rise above the eastern horizon, painting the clouds in shades of pink and orange and gold, remember this fundamental truth. The sun did not rise, you did. The planet beneath you, this ancient sphere of rock and water and air, never stopped turning toward that star. It carried you, along with billions of other humans and trillions of other living things, back into the warmth and light of a new day. And that motion, that eternal rotation, continues even now, even as you rest, even as you close your eyes and drift towards sleep in the darkness. The planet beneath you never moves at exactly the same speed twice through space as it orbits the sun. Earth races forward and slows down, accelerating and decelerating in a cosmic rhythm as it traces an invisible elliptical path that changes every single day of the year. And as we continue this quiet journey together, travelling deeper into the mechanics of celestial motion, exploring the hidden patterns that structure our experience of time, one question naturally emerges from the mathematics, quiet but persistent, demanding an answer. Part 2. Why does the sun speed up and slow down throughout the year? Have you ever noticed, truly noticed with careful attention, that the sun does not keep perfect time? That its motion through the sky is not as regular as a clock? Some mornings, if you watch closely, the sun rises a few minutes earlier than the calendar suggests it should, appearing above the horizon before the predicted moment. Other evenings, it seems to linger stubbornly above the horizon, setting just a bit later than expected, refusing to slip below the edge of the world at the appointed time. Even the most precise mechanical clock ever crafted, even the finest Swiss chronometer made with gears machined to tolerances of microns, wound with springs calibrated to perfection. Even such a masterpiece of engineering cannot perfectly track the sun's apparent motion through the sky across an entire year. Day after day, small discrepancies appear between solar time and clock time. Minutes gained here, minutes lost there. Time that seems to slip mysteriously between the gears of our instruments, as if the sun itself refuses to obey the steady rhythm we try to impose upon it. But here is the truth, and it is beautiful in its elegant simplicity. It is not the sun that changes its pace through the heavens, it is the earth. Our planet, this world we call home, this sphere we inhabit, does not orbit the sun in a perfect circle. It follows an ellipse instead, a slightly stretched oval path, a shape that looks almost like a circle but is subtly elongated. This fundamental fact about Earth's orbit was first described mathematically by the brilliant German astronomer and mathematician Johannes Kepler in the year 1609, after years of painstaking analysis of observational data. Kepler's discovery changed everything humanity understood about the cosmos. By carefully analysing decades of extraordinarily precise observations recorded by the Danish astronomer Tycho Brahe, who had spent his life measuring the positions of planets with an accuracy previously thought impossible, Kepler realised something revolutionary. The planets did not move in the perfect circles that philosophers and astronomers had assumed for more than 2,000 years since the time of ancient Greece. They moved in ellipses instead, with the sun located not at the centre of those ellipses, but at one of the two focal points of the elliptical shape. This insight, this revelation about the true geometry of the solar system, became known as Kepler's first law of planetary motion. It shattered 2 millennia of astronomical thought in a single stroke. But it was his second law that revealed something even more profound, even more fundamental, about how planets actually move through space over time. It is instead a graceful, rhythmic acceleration and deceleration, a cosmic pulse that quickens and slows with beautiful regularity, a dance between gravity and momentum that repeats every year with astonishing precision. For Earth specifically, this means our distance from the Sun changes constantly throughout the year. We are never at exactly the same distance twice. In early January, typically around the 2nd or 3rd day of the year, Earth reaches perihelion, its closest point to the Sun along the entire orbit. At that special moment, we are approximately 147 million kilometers away from that burning sphere of hydrogen and helium, fusing atoms in its core. 6 months later, in early July, around the 4th or 5th day of the month, Earth reaches aphelion, its farthest point from the Sun. At that moment, we are about 152 million kilometers distant. That difference between perihelion and aphelion, just 5 million kilometers out of a mean orbital distance of approximately 150 million kilometers, might seem trivial at first glance. It represents only about 3% variation in distance, barely more than the thickness of a line on most diagrams of the solar system. But across the vast scales of the solar system, across distances that light takes 8 minutes to traverse, that small change in distance transforms everything about the rhythm of our sky. The apparent motion of the sun across the heavens, and the subtle variations in day length we experience throughout the year. When Earth approaches perihelion in January, racing toward its closest point to the Sun, its orbital speed increases significantly according to Kepler's second law. At this moment, we are travelling at approximately 30.3 kilometers per second through space. That translates to more than 109,000 kilometers per hour, faster than most people can truly comprehend or visualize. It is a speed so tremendous that if you could somehow stand still in space and watch Earth pass by, it would cross its own diameter, nearly 13,000 kilometers, in less than 7 minutes. The entire planet would rush past you in the time it takes to watch a short video. 6 months later, at aphelion, in July, when we have swung out to our farthest point from the Sun, our orbital speed decreases to roughly 29.3 kilometers per second, about 105,000 kilometers per hour. We have slowed down by a full kilometer per second, a difference of about 3,600 kilometers per hour. That might not sound like much compared to the total velocity, but maintained over weeks and months as Earth travels millions of kilometers through space, it fundamentally, dramatically reshapes the apparent motion of the sun as we see it from Earth's surface. It makes our days stretch and contract in subtle but measurable ways, creating a pattern that ancient astronomers could observe with nothing more than shadows and patience, but could not fully explain without understanding the true geometry of the solar system. This effect, this persistent discrepancy between where the sun actually is in the sky and where our clocks tell us it should be, has a name in astronomy and celestial mechanics. Scientists call it the equation of time. Despite the name, it is not really an equation in the sense of something you solve. It is rather a correction, a function that varies throughout the year, showing the difference between apparent solar time, the actual position of the sun in your local sky, and mean solar time, the averaged, smoothed out time that we use for our clocks and schedules. The equation of time is one of the most quietly fascinating, most beautifully complex concepts in all of celestial mechanics. It is a mathematical relationship that explains why solar time and clock time are never perfectly aligned, why sundials and watches always disagree by at least a few minutes, no matter how accurately both are made, and why that disagreement changes throughout the year in a predictable, repeating pattern that has remained constant for millions of years. Imagine for a moment that you were to measure time purely by the sun's position in the sky, ignoring all clocks and watches and phones, living by the rhythm of the star that sustains all life on Earth. You might define noon as the precise moment when the sun crosses the meridian, that imaginary line running from due north through the point directly above your head, called the zenith, down to due south. This is true solar noon, the moment when the sun reaches its highest point in the sky for that day, when shadows are shortest, when the sun's rays strike your location most directly. If you measured this moment carefully every single day for an entire year, perhaps by noting the exact instant when a vertical pole casts its shortest shadow and compared it to your watch, to the standard civil time we all use for coordinating our lives, you would discover something strange. A small but persistent discrepancy would appear. Sometimes the sun would cross the meridian early, arriving at that highest point several minutes before 12 noon according to your watch. Sometimes it would arrive late, not crossing until several minutes after clock noon. The sun, it seems, does not run on schedule. Over the course of an entire year, as you accumulated these measurements day after day, that difference between solar noon and clock noon would vary in a specific pattern, growing and shrinking rhythmically. At some times of year, the sun would be as much as 16 minutes ahead of clock time, crossing the meridian well before noon on your watch. At other times, it would be as much as 14 minutes behind, arriving late to its appointment with the meridian. This represents a total variation of about 30 minutes across the year, a half hour that slips back and forth between the sun and our clocks. This remarkable variation happens because of two distinct factors working together, two separate effects that combine and interfere with each other to create the complex pattern we observe. The first factor, which we have already explored, is Earth's elliptical orbit. The changing speed of Earth along its path causes the sun's apparent motion against the background stars to vary throughout the year. When we move fast in January, the sun appears to move faster eastward through the constellations. When we move slower in July, the sun's apparent motion slows correspondingly. The second factor is the tilt of Earth's rotational axis, that 23.5-degree angle that gives us seasons and makes the sun's path across the sky change dramatically throughout the year. This tilt creates an additional effect on the equation of time because of how we define solar time and measure the sun's progress across the sky. The sun does not move along the celestial equator, that imaginary line in the sky directly above Earth's equator. Instead, because of the tilt, the sun moves along a different path called the ecliptic, which is tilted relative to the celestial equator by 23.5 degrees. As the sun moves along this tilted ecliptic throughout the year, its apparent speed along the celestial equator, which is what actually matters for timekeeping, varies. When the sun is far from the celestial equator, during the summer and winter solstices in late June and late December, its daily motion has a larger component parallel to the celestial equator. It appears to move faster in terms of the celestial coordinates we use to measure time. When it is close to the celestial equator, During the spring and autumn equinoxes in late March and late September, its motion is more perpendicular to the equator, giving it a smaller component of motion in the direction that matters for timekeeping. It appears to move slower. This effect combines with the variation in Earth's orbital speed to create a complex but beautifully predictable pattern that repeats every single year with metronomic regularity. Together, the elliptical orbit and the axial tilt make the solar day, the true time between consecutive noons measured by the sun's actual position, slightly longer or shorter than exactly 24 hours at different times of year. In early January, when we move fastest around the sun, each true solar day lasts a little longer than the average 24 hours we have agreed to use for our clocks. The sun appears to move more quickly eastward against the background stars, and Earth must rotate a bit extra, completing more than 360 degrees of rotation to bring the sun back to the meridian again. Around early July, when Earth moves slowest through its orbit, the opposite happens. Each solar day becomes slightly shorter than average. The sun's apparent motion through the sky slows down, and Earth doesn't need to rotate quite as much to bring the sun back to the meridian. These variations are small on a daily basis, typically just a few seconds per day, but they compound over time. Day after day, week after week, those seconds accumulate into minutes, and those minutes accumulate into the full 30-minute variation we observe over the course of a year. The difference in length from one solar day to the next can be as much as 30 seconds, which might not seem significant in isolation when you are living your daily life. But that 30 seconds compounds relentlessly over time. If you were to set a perfect clock to match the sun at solar noon on one particular day and then never adjust it, within a week it would be off by several minutes. Within a month it might be 15 or 20 minutes fast or slow depending on the time of year. Within 6 months it could be wrong by a quarter of an hour or more. This is precisely why sundials, which are fundamentally accurate devices that directly measure the sun's true position using nothing more than a shadow cast by a vertical stick or triangular plate, do not always match your phone's clock or your wristwatch. This elegant shape has its own name in astronomy. It is called an analemma. If you were patient enough to photograph the sun at exactly the same time every day for an entire year, from exactly the same location, using a camera mounted on a fixed tripod that never moves, you would see the sun trace out this figure 8 pattern against the sky. This would happen because the sun's position varies both north-south due to the seasonal tilt and east-west due to the equation of time. The north-south motion creates the vertical stretch of the figure 8, with the sun high in summer and low in winter. The east-west motion creates the horizontal width, with the sun ahead of or behind its average position at different times of year. Together they create that characteristic loop, that cosmic figure 8, visible to anyone patient enough to document it. The analemma appears on some globes and maps, sometimes as that mysterious elongated figure 8 shape marked somewhere over the Pacific Ocean. Many people who see it never understand what it represents. They assume it is some kind of decoration or perhaps a navigation marking. But now you know the truth. It is the path of the sun through the sky across one full year when observed at the same moment each day from the same spot on Earth's surface. It is physics made visible, time made tangible. The complex interaction between Earth's elliptical orbit and its tilted axis rendered in light against the dome of the sky. Ancient civilizations struggled with these variations long before they understood their cause. They built calendars based on the sun's motion, carefully tracking its position day after day across the seasons, but found to their frustration that the sun did not cooperate with their neat divisions of time into equal days. The Babylonians in Mesopotamia, the Egyptians along the Nile, the Maya in Central America, cultures separated by thousands of kilometers and centuries of time, all developed sophisticated systems to track the sun's changing position and predict when seasons would shift, when floods would come, when it was safe to plant crops or set out on long journeys. They knew, though they could not explain why, that time was slippery, that the sun's motion through the sky did not match the simple rhythm of days counted one after another like beads on a string. They knew that some months the sun moved faster and some months slower. They built elaborate correction systems into their calendars, adding intercalary months or days to keep the calendar aligned with the seasons, making adjustments every few years to prevent drift. Today, NASA and other space agencies around the world must account for the equation of time when planning satellite orbits and spacecraft missions with extraordinary precision. Every launch window, every moment when it is possible to launch a spacecraft from Earth's surface toward another planet or moon, is calculated not by the clock on the wall, but by the Sun's true position relative to Earth's rotation at that specific moment. Mission planners must know exactly where Earth is in its orbit, how fast it is moving, and what time it really is according to solar position, not just clock time. Even a 1-second discrepancy in timing, one single tick of the clock, can shift a spacecraft's trajectory by hundreds of kilometers, potentially causing the mission to miss its target entirely or requiring costly mid-course corrections that burn precious fuel. In that sense, the equation of time is not merely an interesting astronomical curiosity, a quirk of celestial mechanics that makes for good conversation at planetariums. It is a practical, essential correction that enables modern space exploration, that allows us to send robots to Mars and Venus and Jupiter with confidence that they will arrive where we intend them to. The International Space Station, that marvel of engineering orbiting 400 kilometers above Earth's surface in the thin upper reaches of the atmosphere, completes one full orbit every 90 minutes, racing around the planet at more than 27,000 kilometers per hour. Astronauts aboard the station see 16 sunrises and 16 sunsets every 24 hours, a complete day-night cycle every 90 minutes. Their experience of day and night is completely disconnected from the surface far below, where people experience the normal 24-hour rhythm. And yet, even their orbit, even that precisely calculated path through space maintained by periodic rocket firings and constant adjustments, must account for the equation of time and the variations in Earth's rotation and orbital speed that change how the planet moves through space from day to day and season to season. Flight controllers must know Earth's exact orientation, its precise rotational position, to communicate with the station through ground antennas. They must account for every variation, every wobble, every tiny change in rotation rate caused by winds and earthquakes and ocean currents. Carl Sagan, that eloquent explorer of the cosmos, once wrote with characteristic poetry, "We are made of star stuff." He was referring to the fact that every atom in our bodies heavier than hydrogen and helium was forged in the nuclear furnaces of stars that died long before our sun was born. But we are also made of time in a very real sense, shaped by rhythms that flow from the mechanics of orbits and rotations, from the ellipse Earth traces around the sun and the wobble of its axis through space, from the equation of time and the complex dance of celestial mechanics. These are not abstract concepts disconnected from daily life. They are the foundations of your experience of the world, the hidden clockwork behind every sunrise and sunset you have ever witnessed, every season you have lived through, every moment you have experienced. When you notice the sun rising earlier in summer or setting later in winter, when you observe that December afternoons feel short and dark while June evenings stretch on bright and warm, remember that you are witnessing the equation of time in action, combined with the changing seasons. You are seeing the effects of Earth's elliptical orbit and its tilted axis, two simple geometrical facts that transform the steady rotation of a planet into the complex, beautiful dance of changing daylight we experience throughout the year. It is a powerful reminder that time is not as simple as we often think, that duration and motion are intimately, fundamentally connected, that the universe keeps time in its own way, according to laws of physics that care absolutely nothing for our human convenience or our desire for regularity, but which create nonetheless a pattern of such profound beauty and such reliable regularity that we can predict the sun's position thousands of years into the future with remarkable, almost miraculous accuracy. And this brings us to something even more profound, even more fundamental to our experience of life on Earth. The planet does not merely spin at varying speeds relative to the sun as it races through its elliptical orbit. The Earth itself is tilted at an angle, leaning into the void of space like a spinning top that has begun to wobble. And this tilt creates one of the most fundamental patterns governing all life on this world, the rhythm we call the seasons. But before we can truly understand seasons, before we can appreciate why summer is hot and winter is cold, Why days are long in June and short in December, we must first understand the invisible geometry behind them, the subtle angle of 23.5 degrees that makes summer and winter possible at all. Part 3. The tilt that makes the seasons. There is an angle written into the fundamental structure of our world. 23.4 degrees. That is how far Earth's rotational axis leans relative to the plane of its orbit around the Sun. It is not a large angle by any measure, less than a quarter of a right angle, less than a third of the angle between north and northeast on a compass. A tilt so subtle you would barely notice it if you held a model globe of Earth in your hands and measured it with a protractor. And yet, that single angle, that one geometric parameter, is directly responsible for almost everything we experience as the rhythm of the year, the patterns that structure both nature and civilization. Seasons. The changing length of days. The arc of the sun across the sky from low in winter to high in summer. The migration of birds between continents. The blooming of flowers in sequence from snowdrops in early spring to asters in late autumn. The cycles of planting and harvest that feed human civilization. All of it, every bit of the yearly rhythm that gives Earth its character and makes life possible in its current form, flows from this one geometric fact, this 23.4 degree tilt. If Earth's axis were perfectly perpendicular to its orbital plane, if it stood straight up and down without any tilt at all relative to the flat disk of the solar system, our world would be utterly, fundamentally different. The sun would rise and set at exactly the same time every single day, year after year, millennium after millennium, with no variation whatsoever. Noon would always find the sun at exactly the same height above the horizon for any given location. The equator would still receive the most direct sunlight, as it does in our current tilted reality. But every other latitude, from the tropics to the poles, would receive exactly the same amount of light and warmth year-round, unchanging across the centuries. There would be no seasons under such conditions. No spring thaw when ice melts and rivers flow and bears emerge from hibernation. No summer heat driving you to seek shade and cool water. No autumn harvest when leaves turn gold and crops are gathered before winter. No winter cold forcing animals to shelter and humans to light fires and wrap themselves in warm clothing. Just an eternal sameness, an endless repetition of identical days, each precisely like the one before and the one after. The climate at any given location would be constant, eternally spring perhaps, or eternally autumn depending on the latitude, but unchanging, monotonous, static. But Earth does not stand upright like a soldier at attention. It leans at this crucial angle of 23.4 degrees. And because of that lean, that tilt of the rotational axis away from perpendicular, as our planet completes its yearly orbit around the sun, different parts of the surface tilt toward or away from that burning star at different times of the year. Sometimes the northern hemisphere points toward the sun, sometimes the southern hemisphere, sometimes neither, during the brief transitional moments when the tilt is sideways relative to the sun. This creates seasons, not, as many people mistakenly believe throughout history and even today, because Earth moves closer to or farther from the sun at different times of year, but because the angle of sunlight striking any given part of the surface changes dramatically over the course of 12 months. The distance variation of 5 million kilometers between perihelion and aphelion, which we discussed earlier, actually plays almost no role in creating seasons. In fact, Earth is closest to the sun in January, which is winter in the northern hemisphere, completely opposite to what you would expect if distance determined seasons. Instead, it is all about angle. The angle at which sunlight strikes the surface. The angle the sun makes with the horizon. The path the sun traces across the sky from dawn to dusk. All of this changes because of the tilt, and that changing angle makes all the difference between summer heat and winter cold. Right now, at this exact moment, the northern end of Earth's rotational axis points toward a particular direction in space, almost exactly toward the star Polaris, also known as the North Star or Pole Star. This direction in space is fixed, at least over timescales of human lifetimes, because of the conservation of angular momentum. A spinning object maintains the orientation of its axis unless acted upon by an external torque, an external twisting force. Earth experiences some external torques from the Sun and Moon, which cause that slow 26,000-year precession we mentioned earlier, but over days or years or even centuries, the axis points essentially in the same direction. 6 months from now, Earth will be on the opposite side of its orbit around the Sun, 180 degrees away, 150 million kilometers distant across the Sun itself. The axis will still point in exactly the same direction in space, toward Polaris and the constellation Ursa Minor, because the tilt itself does not change. The orientation remains fixed. But now, because Earth has moved halfway around its orbit, that same unchanging tilt has a completely different relationship to the incoming sunlight. Now the axis points the northern hemisphere away from the Sun instead of toward it. The geometry has inverted. What was tilted toward the Sun in June is tilted away in December. What pointed toward warmth now points toward cold. And this inversion, this complete reversal of the relationship between tilt and sunlight, creates the opposite season. Summer becomes winter. Winter becomes summer. The hemispheres trade places in the cosmic dance. This is the key, the crucial insight to understanding seasons. The tilt does not change. The direction Earth's axis points in space remains absolutely fixed, at least over timescales of years. What changes is Earth's position along its orbit, and as that position shifts through 360 degrees over 12 months, the relationship between the tilted axis and the incoming sunlight transforms completely from one extreme to the other and back again. During the June solstice, occurring around the 20th or 21st of June each year, the northern hemisphere tilts as far toward the Sun as it ever does during the entire orbital period. The North Pole, that point at 90 degrees north latitude where all lines of longitude meet, leans directly toward the Sun at this moment. This is summer in the north, the season of warmth and long days. The Sun rises high in the sky, climbing to an elevation angle that depends on your specific latitude, but is always at its maximum for the year. Its rays strike the ground at a steep angle, coming almost straight down at noon in high northern latitudes, concentrating their energy on a small surface area. The days are long during this season, stretching past 14 hours in mid-latitudes like New York or Paris, past 16 hours in cities like London or Berlin, and approaching 24 hours of continuous daylight in places like Stockholm or Oslo. Above the Arctic Circle, that special latitude at approximately 66.5 degrees north, where the tilt angle equals the latitude, the Sun does not set at all for days or weeks. It circles the sky continuously, dipping toward the northern horizon at midnight, but never falling below it, creating the midnight sun, that strange and beautiful phenomenon where daylight becomes a constant presence, where night ceases to exist temporarily, and time loses one of its most fundamental markers. At the exact same moment, simultaneously on the other side of the planet, the southern hemisphere tilts away from the Sun at its maximum angle. Winter grips the southern continents. Australia experiences its coldest months. South Africa bundles against the chill. Argentina sees snow in its southern regions. The Sun barely climbs above the horizon even at noon, its rays striking the surface at a shallow, glancing angle that provides little warmth. Days are short, sometimes lasting only 8 or 9 hours from sunrise to sunset in mid-latitudes. Nights are correspondingly long and cold, sometimes 15 or 16 hours of darkness. Below the Antarctic Circle, at 66.5 degrees south, the Sun does not rise at all for weeks or months depending on the exact latitude. Darkness becomes total, except for twilight at midday if you are near the circle's boundary. The only light comes from stars scattered across the black dome of the sky, from the moon if it happens to be above the horizon, and from the occasionally shimmering dance of the aurora australis, the southern lights created when charged particles from the Sun collide with Earth's magnetic field and atmosphere, painting the darkness with curtains of green and red and purple light. 6 months later, around December 21st or 22nd, Earth has completed half of its orbit, 180 degrees around the Sun. Now the situation inverts completely. The southern hemisphere tilts toward the Sun at maximum angle. Summer arrives in Sydney and Cape Town and Buenos Aires. Beaches fill with people, temperatures soar, days stretch long and bright. Meanwhile, winter settles over the northern hemisphere. New York and London and Tokyo experience their coldest, darkest days. Snow falls. People wear heavy coats and light fires to stay warm. The sun barely shows itself, rising late and setting early, tracing a low arc across the southern sky. The geometry simply reverses like the swing of a pendulum. The tilt has not changed even slightly. The axis still points toward Polaris in space. But Earth has moved, and that movement inverts the entire relationship between tilt and sunlight, causing the hemispheres to trade seasons. It is elegant, symmetrical, inevitable given the laws of physics and the geometry of the situation. Twice each year, during the spring and autumn equinoxes occurring around March 20th and September 22nd, Earth reaches a special configuration in its orbit. At these precise moments, the axis tilts neither toward nor away from the Sun. Instead, it tilts perpendicular to the line connecting Earth and Sun, sideways relative to the incoming solar radiation. The tilt still exists, of course. The planet still leans at 23.4 degrees. But at these specific points in the orbit, that tilt is oriented 90 degrees away from the Sun, meaning it has no effect on which hemisphere receives more direct sunlight. At these special moments, remarkable things happen. Day and night become approximately equal in length everywhere on Earth, from the North Pole to the South Pole, and everywhere in between. The word equinox literally means equal night in Latin, from equus meaning equal and nox meaning night. The Sun rises precisely due east, exactly at 90 degrees on the compass, and sets precisely due west at 270 degrees. It passes directly overhead at the equator at noon, reaching the zenith, making the Sun's rays fall perfectly perpendicular to the surface there. And for just these brief times, just a few days twice each year, the entire planet shares essentially the same balance of light and darkness. Someone in Alaska experiences roughly 12 hours of day and 12 hours of night, the same as someone in Singapore, the same as someone in Australia. The usual extreme differences between latitudes temporarily vanish. The whole world equalizes. But this balance, this brief moment of equality, does not last long. Within days, sometimes within hours, the tilt begins to assert itself again in full force. The axis orientation that was briefly neutral relative to the Sun shifts back to favoring one hemisphere or the other as Earth continues its inexorable motion around its orbit. In the northern hemisphere, after the March equinox, days immediately begin growing longer and nights shorter as the North Pole tilts increasingly toward the Sun with each passing day. After the September equinox, the reverse happens. Days immediately begin shortening, nights lengthen. The cycle continues forward, driven by nothing more than geometry and motion, orbit and tilt combined into an eternal dance. The amount of sunlight a location receives depends not just on how many hours the Sun remains visible above the horizon, though that certainly matters greatly. It also depends critically on the angle at which that sunlight strikes the surface, the elevation angle of the Sun in the sky, the steepness of the ray's path through the atmosphere. During summer, when your hemisphere tilts toward the Sun, sunlight arrives nearly straight down at noon, especially if you live in the tropics or subtropics. The rays concentrate their energy on a small area of ground, heating it efficiently and intensely. Each square meter of surface receives a large amount of solar energy. During winter, by contrast, the same rays of light from the same Sun arrive at a shallow angle, glancing across the land rather than hitting it directly from above. This spreading effect means the same amount of light energy that heated 1 square meter in summer now spreads over 2 or 3 or even 4 square meters in winter, depending on the exact latitude and the Sun's elevation angle. The energy per unit area, the amount of warming per square meter of ground, drops dramatically even though the total amount of sunlight coming from the Sun has not changed at all. This angle effect is far more important than day length in most locations. Even if winter days and summer days were exactly the same length, which they are not, winter would still be cold and summer hot purely because of the angle difference. This is why the tropics remain warm year-round. Near the equator, between the Tropic of Cancer at 23.4 degrees north and the Tropic of Capricorn at 23.4 degrees south, the sun is always high in the sky at noon throughout the entire year, always striking the surface at a steep angle that concentrates its energy effectively. The tilt of Earth's axis matters less near the equator because the equator lies along the plane of Earth's rotation, always perpendicular to the axis by definition. The sun does shift slightly north and south of the equator throughout the year, crossing it at each equinox and reaching its maximum northern or southern position at each solstice. But it never strays far enough from the equatorial region to dramatically change the amount of solar energy reaching tropical locations. The variation exists but is modest, typically only 10 or 20% between the most and least sunny times of year. This is why many tropical regions do not experience seasons in the temperature sense at all. Instead, they experience wet and dry seasons driven by atmospheric circulation patterns, but the temperature remains warm to hot year-round. But in higher latitudes, far from the equator in places like northern Canada or Norway or Patagonia or New Zealand, the tilt dominates the entire climate. The difference in sun angle across the year is dramatic, often 40 degrees or more between summer and winter. Summer sun. Summer sun can heat the land intensely during the long days when it climbs high into the sky, sometimes reaching elevation angles of 60 or even 70 degrees in far northern locations during June. Winter sun barely clears the horizon even at noon, perhaps reaching only 15 or 20 degrees of elevation in December, providing almost no warmth at all during the brief hours it manages to appear. Scientists measure this relationship precisely using a concept called solar insolation, which refers to the amount of solar energy received per unit area at the surface. Insolation depends on both the sun's elevation angle and the length of time it remains above the horizon, combined into a single measure of total energy delivered. NASA satellites continuously measure insolation at every point on Earth's surface, using instruments that detect incoming solar radiation across the entire electromagnetic spectrum, from ultraviolet through visible light to infrared heat. These measurements create detailed maps that show exactly how much energy each region receives throughout the year, down to individual days and even hours. The data confirms precisely what the geometry predicts. Seasonal variations in insolation are small near the equator, perhaps varying by 20 or 30% between the sunniest and least sunny months. But near the poles, the variation is enormous, often by factors of 10 or even infinity if you compare summer to polar night when the sun does not rise at all. This tilt, this precise angle of 23.4 degrees, has been stable for hundreds of millions of years at least, held firmly in place by the gravitational influence of the Moon. Our large natural satellite, the Moon, stabilizes Earth's rotation through tidal forces, preventing the axis from wobbling chaotically over geological time, as happens with Mars, a planet with no large moon to anchor its rotation. Mars has two small moons, Phobos and Deimos, but they are tiny, more like captured asteroids than proper moons. They exert almost no stabilizing influence on Mars's rotation. As a result, Mars's axial tilt varies dramatically over timescales of tens or hundreds of thousands of years, sometimes remaining near 25 degrees like Earth's current tilt, but sometimes swinging wildly to 40 degrees or more, possibly even reaching 60 degrees during extreme excursions. This makes Mars's climate wildly unstable over geological time, with ice ages and warm periods alternating chaotically, making the development of complex life essentially impossible even if liquid water and other necessary ingredients were present. Earth's stable tilt, maintained by the Moon's gravitational anchor, has allowed life to flourish under predictable seasonal patterns for billions of years. Plants and animals evolved to anticipate these reliable rhythms burned deep into their DNA. Deciduous trees drop their leaves in autumn in preparation for winter, conserving water and energy when photosynthesis becomes difficult. They bud again in spring when warmth and light return. Annual plants complete their entire life cycles in a single growing season, surviving winter as seeds. Migration patterns developed over millions of years, allowing birds and whales and caribou to move between summer feeding grounds and winter shelters, traveling thousands of kilometers following the changing seasons. Hibernation strategies emerged in mammals and reptiles and insects, allowing them to survive months of cold and scarcity by lowering their metabolism to barely detectable levels, sometimes appearing nearly dead while winter passes above them. Entire ecosystems structured themselves around the reliable advance and retreat of seasons, creating food webs and predator-prey relationships that depend on the predictable timing of spring growth and autumn harvest. Imagine, just for a moment, if our axis suddenly tilted to 40 degrees, as Mars sometimes experiences over its chaotic history. Winters would become far more extreme, especially in higher latitudes, which would be plunged into even deeper, colder darkness for even longer periods. Summers would scorch regions that currently enjoy moderate, comfortable climates, turning temperate zones into near deserts during the hottest months. The ice caps would grow and shrink dramatically with the extreme seasonal variations, perhaps covering much of the northern continent in ice during winter and retreating almost entirely during summer. Weather patterns would destabilize as the increased temperature gradient between equator and poles drove more violent storms and more extreme atmospheric circulation. Food chains would begin to collapse as species failed to adapt quickly enough to the changing conditions, unable to evolve fast enough to keep pace with environments that shifted far beyond their tolerance ranges within a few generations. The stable climate that enabled civilization to develop would disappear, replaced by chaos. But instead, mercifully, Earth's tilt remains nearly constant across human timescales, and indeed across timescales of millions of years, wobbling only through that slow 26,000-year precession cycle we discussed earlier. This stability, this reliability, is one of the fundamental reasons Earth remains habitable generation after generation, century after century, millennium after millennium. It is one of many Goldilocks factors, conditions that are not too extreme in either direction, but just right for life to flourish, that make our planet a rare oasis in the cosmic desert. Ancient peoples across the globe knew that the solstices and equinoxes were special days without understanding the physics behind them. They marked these days with monuments and rituals and celebrations that endured for centuries. Stonehenge in southern England, that mysterious circle of massive standing stones erected perhaps 5,000 years ago, aligns perfectly with the sunrise on the summer solstice. On that one day each year, the longest day, people can stand at the centre of the monument and watch the sun rise directly over a specific stone called the heel stone, the light streaming between the great trilithons to illuminate the heart of the circle. Thousands of years ago, when Stonehenge was in active use by the Neolithic peoples who built it through tremendous labour over many generations, they gathered there to watch that sunrise, marking the turning point of the year when the sun reached its farthest north and began its retreat toward winter again. Why they did this, what religious or cultural significance the solstice held for them, we can only guess. But the astronomical knowledge encoded in stone is undeniable. Similar monuments exist on every inhabited continent, built by cultures separated by vast oceans and thousands of years, yet all focusing on these same crucial moments in Earth's orbit. Newgrange in Ireland, a passage tomb older than the pyramids, is designed so that sunlight penetrates deep into its central chamber only during the few days around the winter solstice, illuminating the darkness at the moment of the year's longest night. The pyramids of Egypt align with cardinal directions and encode astronomical knowledge about the cycles of stars and seasons. The Sun Temple at Mesa Verde in Colorado, built by ancestral Puebloans, marks solstices and equinoxes through carefully placed windows and shadows. Angkor Wat in Cambodia. That massive temple complex built in the 12th century aligns with the spring equinox sunrise, the sun appearing directly in the centre of the main tower when viewed from a specific location, a feat of architectural astronomy that required sophisticated understanding of Earth's motion. The Temple of Kukulkan at Chichen Itza in Mexico, a Mayan pyramid, creates a serpent of shadow and light descending its stairs during the equinoxes, a cosmic spectacle that draws thousands of visitors even today. Cultures separated by oceans and millennia, and languages and belief systems all looked up at the same sky, noticed the same patterns of tilted Earth creating seasons, and built structures to honor that tilt and its consequences. They did not understand the physics in the modern sense, did not know about orbits and rotational axes and gravitational mechanics, but they understood the consequences intimately, in ways perhaps deeper than our modern scientific understanding. They knew when to plant crops and when to harvest. They knew when herds would migrate and when rivers would flood. They knew in their bones and their traditions and their accumulated wisdom of generations that the sun followed a pattern, a cosmic rhythm that repeated with astonishing regularity year after year, century after century, reliable beyond any human promise or guarantee. Today, we understand the mechanism behind that rhythm with mathematical precision. We can calculate Earth's position in its orbit at any moment in history or any moment in the future. We can predict solstices and equinoxes thousands of years ahead, or determine when they occurred in ancient times. We can explain why the sun reaches its highest point in the sky on one specific day and its lowest on another. We know that Earth's tilt creates seasons because of the changing angle of sunlight and the changing length of days, both of which flow mathematically from that 23.4 degree tilt. We have mathematical models verified by satellite data and centuries of careful observation from observatories around the world. And yet, remarkably, the experience remains fundamentally the same as it was for our ancient ancestors. When spring arrives and flowers bloom, when summer stretches the days into long, warm evenings, perfect for gathering outside, when autumn paints the leaves in colours of gold and crimson and orange, as chlorophyll breaks down and other pigments emerge, when winter brings cold and forces us to gather around fires and tell stories to pass the long dark nights, we are experiencing exactly what our ancestors experienced thousands of years ago. The same tilt, the same orbit, the same geometry of sunlight and shadow playing across the surface of this tilted, spinning, orbiting world we call home. There is something deeply moving, something almost spiritual, about that continuity across time and culture. The universe operates according to laws that do not change with human culture or belief or wishes. The tilt of Earth's axis is the same for everyone, everywhere, at all times. A fact of geometry and physics that connects every human who has ever lived under changing seasons. From the very first Homo sapiens who walked out of Africa 100,000 years ago, to you, listening to these words right now in whatever place and time you happen to be. And that tilt, that simple angle, does something else remarkable beyond just creating seasons. It creates a situation where the length of the day, the actual time between sunrise and sunset, changes dramatically depending on both where you are on Earth's surface and what time of year it is. In some places near the equator, that change is subtle and barely noticeable. In other places near the poles, it is profound beyond imagination, creating experiences of time and light that challenge the very concept of day and night. Part 4. Why days lengthen and shorten through the year. The longest day of your life, in terms of hours of sunlight, depends entirely on where you stand on Earth's curved surface. If you live near the equator, within about 10 or 15 degrees of that zero latitude line that circles the middle of the planet, days remain very close to 12 hours long throughout the entire year with minimal variation. The sun rises around 6 in the morning, give or take a few minutes depending on the equation of time we discussed earlier, and sets around 6 in the evening with similar consistency. The variation might be 30 minutes or perhaps 45 minutes between the longest and shortest days, but compared to higher latitudes, this is almost nothing. There is a beautiful consistency, a reliable predictability to life in the tropics when it comes to daylight. Every day feels similar in length to the one before. You always know roughly when the sun will rise and set. You can plan your activities with confidence that darkness will not arrive surprisingly early or that daylight will not linger unexpectedly long. This regularity shapes tropical cultures in subtle ways, influencing when people wake and sleep, when they work and rest, when they socialize and retreat to privacy. But move toward the poles, travel north to Canada or Scandinavia or Alaska, or south to Patagonia or New Zealand's southern regions, and everything changes dramatically, sometimes shockingly so. In higher latitudes, days stretch and compress across the seasons in ways that can seem almost impossible if you have never experienced it, that challenge your fundamental assumptions about the nature of day and night. In Reykjavik, Iceland's capital city located at about 64 degrees north latitude, the sun shines for more than 21 hours during the summer solstice in late June, lighting the sky from just before 3 in the morning until nearly midnight. Only about 3 hours of something resembling night remain, and even then the sky never gets completely dark, remaining in a state of twilight where you can still read a book outside without artificial light. The sun barely dips below the horizon before rising again. But 6 months later, during the winter solstice in late December, the situation inverts utterly. The sun barely appears at all, rising sluggishly around 11 in the morning and setting again by 3 in the afternoon, giving only about 4 hours of dim daylight. The other 20 hours are darkness or deep twilight. The contrast between summer and winter is so extreme that it affects everything from mood to sleep patterns to energy levels to social behavior. Many Icelanders travel south during winter to experience more normal daylight and escape the oppressive darkness. In Tromsø, Norway, an even more extreme location at about 70 degrees north latitude, the phenomenon becomes more dramatic still. The sun does not set at all for approximately 2 months during summer, from about mid-May to the end of July, creating a period called the polar day, or more poetically, the midnight sun. During this time, the sun circles the sky continuously, day and night, rising and falling in height above the horizon, but never dropping below it, never allowing darkness to return, creating a landscape bathed in perpetual golden light even at 3 in the morning. Imagine living through that experience. Imagine waking up at midnight and seeing bright sunlight streaming through your windows. Imagine trying to sleep when your biology tells you it should be dark, but the sky outside is still blue and bright. Imagine the confusion of time, the loss of the usual markers that divide day from night, work from rest, activity from sleep. Many people who live in these latitudes during summer report difficulty sleeping, feeling constantly energized by the light, needing blackout curtains just to trick their bodies into producing the melatonin needed for sleep. And then winter arrives and brings the opposite extreme. The polar night settles over Tromsø, and the sun does not rise at all for about 2 months, from late November through mid-January. It is not total darkness for all 24 hours, because even when the sun is below the horizon, refraction in the atmosphere and the sun's position not far beneath the horizon create twilight around midday, a dim blue glow on the southern horizon that reminds you the sun still exists somewhere beyond the curve of the earth. But direct sunlight does not reach the surface. The sun does not appear, not even for a moment. Imagine waking up in December to darkness, going to work in darkness, returning home in darkness. The sun never appears above the horizon, never shows its face, never provides direct light to the land. Just twilight at best, that faint glow at midday, then darkness again. The stars wheel overhead in the constant night. The moon, when it is above the horizon, provides more light than usual because it has no competition from the sun. Time loses its usual structure. Depression rates increase dramatically during the polar night as people struggle with the lack of sunlight, sometimes requiring light therapy to maintain their mental health and circadian rhythms. This extraordinary variation in day length exists because of the tilt of Earth's axis combined with the spherical geometry of a rotating planet. During the summer solstice in the northern hemisphere, around June 21st, the North Pole tilts 23.4 degrees toward the Sun, its maximum tilt in that direction. This means that as Earth rotates, the entire Arctic region, everything above approximately 66.5 degrees north latitude, never rotates out of the sunlight. That boundary latitude of 66.5 degrees is called the Arctic Circle, and it is defined precisely by the tilt angle. It is the southernmost latitude where the sun can remain above the horizon for 24 continuous hours. For locations exactly on the Arctic Circle, The midnight sun occurs only on the summer solstice itself, just one day each year when the sun barely grazes the northern horizon at midnight without setting. For locations farther north, closer to the pole, the period of midnight sun lasts longer. At 70 degrees north, it lasts about 2 months. At 80 degrees north, almost 4 months. At the North Pole itself, 90 degrees north latitude, the sun rises around the March equinox and does not set again until the September equinox. 6 full months of continuous daylight, followed by 6 full months of continuous darkness. Meanwhile, at the exact same moment, on the same summer solstice day, the South Pole tilts 23.4 degrees away from the sun. Antarctica rotates completely in shadow. The entire continent experiences polar night. For the same 2-month period when Norway basks in the midnight sun, Antarctica endures the polar night, darkness at noon, stars visible all day, temperatures plunging to 100 degrees below 0 Celsius or colder in the interior of that frozen continent. The geometry is perfectly, mathematically symmetrical. Whatever the northern hemisphere experiences in June, the southern hemisphere experiences in December. Whatever summer brings to the north, winter brings to the south, and vice versa. The only asymmetry comes from the fact that the southern hemisphere is primarily ocean, while the northern hemisphere has large land masses at high latitudes, which creates slight differences in how quickly temperatures respond to changing sunlight. But the underlying geometry of day length is perfectly symmetric. At the equinoxes, around March 20th and September 22nd, when Earth's axis tilts neither toward nor away from the sun, this extreme situation normalizes briefly across all latitudes. For a few days, even the poles experience something close to a normal day and night cycle, with the sun rising and setting roughly every 24 hours as seen from the pole, skimming around the horizon in a circle rather than rising and setting in the east-west pattern seen from lower latitudes. But this brief period of normalcy quickly gives way as Earth continues its inexorable motion along its orbit, and the tilt reasserts its overwhelming influence over day lengths at high latitudes. The rate at which day length changes through the year is not constant. It varies depending on both the time of year and your latitude. Near the solstices, around June 21st and December 21st, the rate of change in day length is very slow, almost imperceptible from one day to the next. The longest days of June seem to persist for weeks, each day only a second or two shorter than the previous one. The sun's path through the sky barely changes. Its elevation angle at noon varies by only a few minutes of arc from one day to the next. Ancient peoples noticed this apparent pause in the sun's motion and gave it a name that has persisted for thousands of years. Solstice, from the Latin word sol, meaning sun, and sister, meaning to stand still. For about a week around the summer and winter solstices, the sun's path through the sky seems to stand still, to pause at its highest or lowest point, before reversing direction and beginning its journey back toward the opposite extreme. This pause is not real in the sense that Earth does not actually stop moving. The orbital motion continues without interruption. But the component of that motion that affects the sun's apparent north-south position in the sky, technically called the sun's declination, slows to almost zero near the solstices. The sun reaches its maximum declination of 23.4 degrees north or south and lingers there for several days, changing by less than 1 minute of arc per day before beginning the return journey. But near the equinoxes, around March 20th and September 22nd, the situation changes dramatically. The rate of change in day length accelerates to its maximum. The sun's declination changes most rapidly as it crosses the celestial equator, moving north or south at about 24 minutes of arc per day, the maximum rate of change that occurs during the year. This rapid change in the sun's position translates directly into rapid changes in day length for observers at mid-latitudes. In places like New York or London or Tokyo, at latitudes around 40 degrees north, day length can change by 3 or even 4 minutes per day near the equinoxes. You can actually notice the difference if you pay careful attention, watching sunset shift visibly earlier or later across the horizon from one evening to the next, noticing that darkness arrives noticeably sooner or later than it did just yesterday. This rapid change gives the spring and autumn seasons their characteristic dynamic feeling, their sense of rapid transition and change, as light itself shifts quickly from one extreme toward another. Scientists model these changes in day length using spherical trigonometry and celestial mechanics, equations that account for your specific latitude, the date and time of year, and Earth's rotational geometry. Given any location on Earth and any date, they can calculate exactly to the second how long the sun will remain above the horizon, when it will rise and when it will set, what angle it will reach at noon, and how all these values change from day to day. This calculation is crucial for everything from agriculture, where farmers need to know their growing season length, to solar energy, where engineers must predict how much power solar panels will generate throughout the year, to architecture, where designers position windows and overhangs to maximize natural light in winter and provide shade in summer, to satellite operations, where controllers must know when spacecraft will be in sunlight or shadow. But these mathematical models reveal something else fascinating about how sunlight is distributed across Earth's surface over time. The total amount of sunlight that reaches the top of Earth's atmosphere at any location, integrated over a full year, does not vary nearly as dramatically between latitudes as you might expect. Over a full year, the poles receive almost as much total sunlight as the equator when measured at the top of the atmosphere, before accounting for absorption and scattering. Yes, winter days are shorter at high latitudes, but summer days are proportionally longer. Yes, the sun is lower in the sky on average at high latitudes, but during summer it remains above the horizon much longer to compensate. When you add up all the sunlight across all the days and nights of an entire year, the total is surprisingly similar from equator to pole, varying by perhaps only 30%, despite the dramatic differences in day length and sun angle throughout the year. What changes most dramatically is not the total annual sunlight, but its distribution in time. That sunlight at high latitudes is concentrated into a short summer season, with long days and relatively high sun angles, providing intense but brief warmth. In winter, very little sunlight arrives, concentrated into short days with low sun angles, providing almost no warmth at all. It is not the amount that matters most for climate and seasons. It is how that sunlight is distributed, whether it arrives steadily year-round or in dramatic pulses of summer abundance and winter scarcity. This distribution is precisely why the polar regions remain cold despite receiving reasonable total annual sunlight. The sunlight arrives at such low angles and is concentrated into such a short summer season that the ground never fully warms. Snow and ice reflect much of the sunlight back into space without absorbing it. The short summer cannot melt all the accumulated ice from the long winter. The system reaches an equilibrium where ice persists year-round, creating the polar ice caps and frozen landscapes we associate with the Arctic and Antarctic. This distribution effect is also why seasons lag behind the solstices by 4 to 6 weeks in terms of temperature. The longest day occurs in late June in the Northern Hemisphere, but the hottest weather typically arrives in late July or August, a delay of 4 to 6 weeks. Similarly, the shortest day occurs in late December, but the coldest weather often comes in January or February. This lag exists because the oceans and land have thermal inertia, thermal mass that takes time to heat up and cool down. The sun may be strongest in late June, but the ground and especially the ocean water are still relatively cool from winter and spring. They must absorb solar energy over many weeks to reach their maximum temperature. By the time they finally warm to their peak in late July or August, the sun has already begun its slow decline toward autumn. The ground and water act as buffers, smoothing out the temperature response, delaying it in time relative to the changing sunlight. The same process occurs in reverse during winter. The weakest sunlight comes in late December, but the ground and water retain heat accumulated during summer and autumn. They cool gradually through the following weeks, only reaching their minimum temperature in late January or February, long after the solstice has passed and the sun has already begun its return towards spring. This thermal lag is essential to Earth's climate system, preventing temperature extremes that would occur if the surface responded instantly to changes in solar input. NASA and the National Oceanic and Atmospheric Administration carefully monitor these patterns using satellite-based instruments and thousands of surface weather stations distributed across every continent and ocean. They track how solar energy flows between the sun, the atmosphere, the oceans, and the land, creating detailed energy budgets that account for every watt of power entering and leaving the system. These measurements have revealed that the thermal inertia of the oceans is particularly important on timescales of weeks to months. Water has a much higher specific heat capacity than rock or soil, meaning it takes much more energy to raise the temperature of water by 1 degree than to raise the temperature of rock by the same amount. Additionally, ocean water can mix vertically and horizontally through currents and convection, distributing heat through large volumes rather than concentrating it at the surface. This makes oceans incredibly effective at storing heat during summer and releasing it slowly during winter, moderating coastal climates. In fact, the presence of large bodies of water near your location can completely transform your seasonal experience despite being at a given latitude. Seattle, Washington, and Montreal, Canada are both at similar latitudes, approximately 48 degrees north. According to latitude alone, they should have similar climates and similar seasonal temperature swings. But Seattle, located on the coast of the Pacific Ocean and influenced by prevailing winds from the west that blow across thousands of kilometers of water, experiences extraordinarily mild wet winters where temperatures rarely drop below freezing, and cool summers where temperatures rarely exceed 30 degrees Celsius. The ocean moderates everything, keeping the city in a narrow, comfortable temperature range year-round. Montreal, by contrast, sits deep in the continental interior, far from large bodies of water, surrounded by vast expanses of land that heat quickly in summer and cool quickly in winter. Montreal experiences harsh, cold winters, where temperatures regularly plunge to -20 or even -30 degrees Celsius, requiring heavy winter clothing and snow removal equipment and indoor heating for months. Summers, conversely, can be quite hot, sometimes reaching 35 degrees Celsius, requiring air conditioning. The same latitude produces completely different climates, entirely because of the difference between coastal and continental locations, between proximity to thermal moderators like oceans and their absence. All of this complexity, every bit of these varying patterns of day length and seasonal temperature and climate zones, flows ultimately from that single angle we began with, 23.4 degrees. Without that tilt, without that lean of Earth's rotational axis away from perpendicular to the orbital plane, weather and climate would be utterly different. Simpler in some ways perhaps, without the complex seasonal variations we experience, but far less interesting, far less dynamic, far less conducive to the extraordinary diversity of life that flourishes on this planet. The tilt makes Earth a world of change, of cycles within cycles, of seasons that repeat in pattern but never quite the same way twice, because small variations in weather and ocean currents and atmospheric conditions make each summer slightly different from the last, each winter unique in its particular combination of cold and snow and storms. And somewhere on Earth, always, at every moment, it is solstice or equinox for someone in terms of their experience of sunlight and shadow. Right now, as you listen to these words, someone somewhere is experiencing the longest day of their year, watching the sun circle endlessly in the sky without setting. Someone else on the opposite side of the planet is enduring the shortest day, seeing barely a few hours of dim sunlight before darkness returns for another long night. Someone is watching the sun barely skim the horizon at midnight, that golden disk refusing to set, creating the magical experience of the midnight sun. Someone else is living through months of darkness, using artificial lights, waiting patiently for the sun to return, watching for that first glimpse of light on the horizon that signals the end of the polar night. All of this happening simultaneously, all across the globe, all part of the same geometric pattern traced by Earth's tilted axis and its motion through orbit. All consequences of the same fundamental physics, the same laws of motion and geometry and light. It is a beautiful reminder, a profound truth, that experience is deeply local, determined by where you stand on this spherical planet, but the physics underlying that experience is absolutely universal. What you see from your window, the length of your day, the angle of your shadows, the path of the sun across your sky. All of it is written by your specific latitude and the current time of year, the moment in Earth's orbit. But the same rules apply everywhere without exception, from the equator to the poles, from the past reaching back millions of years to the future extending millions of years ahead. Earth spins on its tilted axis. Earth orbits the sun. And from those two simple facts, those two fundamental motions, emerges the entire intricate rhythm of changing daylight that structures virtually all life on this planet, from bacteria to plants to insects to mammals to humans. Yet there is more to discover about motion, more layers to uncover in this cosmic dance. Because while Earth spins and tilts and orbits with such reliable regularity, creating the patterns we have explored, all of this motion requires something. It requires momentum, tremendous, almost incomprehensible momentum. And changing that momentum, speeding up or slowing down or deflecting this massive planet from its path, would require forces of staggering magnitude. The question naturally emerges, quiet but persistent. What keeps Earth moving at all? Why does it continue year after year, epoch after epoch without slowing down? And could it ever stop? Part 5. What keeps Earth moving around the sun? Imagine, just for a moment, trying to stop Earth in its orbit. Not just slowing it slightly, but actually halting it completely, bringing this entire planet, all 6 septillion kilograms of rock and metal and water and air and life, to a complete stop mid-flight as it races around the sun at 108,000 kilometers per hour. Try to conceive of what such a force would even look like, what magnitude of power it would require, what kind of engine or brake or mechanism could possibly apply that much force to an entire planet. The answer is almost incomprehensible to human minds evolved to understand forces measured in newtons or kilonewtons, forces we can push with our hands or lift with our backs or generate with machines we can build. It would take more energy than humanity has generated in all of recorded history, all the coal burned, all the oil pumped, all the nuclear reactions detonated or controlled. It would require more energy than all nuclear weapons ever built by all nations combined, if they were somehow detonated simultaneously in a perfect configuration to slow Earth's motion. More energy even than the sun itself outputs over several days of continuous fusion, converting millions of tons of hydrogen into helium every second. Earth's orbital momentum is so vast, so fundamentally enormous, almost unimaginable in scale, that stopping it is not merely difficult or impractical. It is essentially impossible by any means available to physics as we understand it, short of a collision with another planet-sized object travelling at relativistic speeds, an event that would not merely stop Earth but would completely destroy it, vaporizing the crust and breaking the planet into billions of fragments that would scatter across the solar system. And yet, paradoxically, beautifully, Earth requires absolutely no energy to maintain its orbit. None at all. Zero. It simply continues coasting through the vacuum of space, held in its elliptical path, not by any engine or thrust or expenditure of fuel, but by the perfect, elegant balance between two fundamental forces that have been acting on this planet since its formation 4.5 billion years ago. Gravity pulling inward toward the sun, inertia carrying Earth forward tangentially along its orbital path. This is one of Isaac Newton's great insights, one of the foundational principles of physics that revolutionized our understanding of motion in the 17th century. His first law of motion, sometimes called the law of inertia, states with elegant simplicity that an object in motion stays in motion with the same speed and in the same direction, unless acted upon by an external force. Earth is in motion, has been in motion since the solar system coalesced from a rotating disk of gas and dust surrounding the young sun, and will remain in motion essentially forever because space is nearly a perfect vacuum. There is no air resistance in space, no friction between Earth and the medium it moves through, because there is no medium. The space between planets contains some scattered atoms of hydrogen and helium, occasional dust grains, the solar wind of charged particles streaming outward from the sun, but the density is so incredibly low, averaging perhaps 5 atoms per cubic centimetre, that the drag force is utterly negligible. For practical purposes, Earth moves through perfect emptiness. Once set spinning and orbiting in the early solar system, by the angular momentum of the collapsing dust cloud that formed it, by the aggregation of countless smaller planetesimals that collided and stuck together, Earth simply kept going without any need for continuous propulsion. Its momentum, that product of mass and velocity, conserved across geological ages, maintained without effort, persisting because nothing in the vacuum of space can slow it down. Gravity from the Sun provides what physicists call the centripetal force, the inward directed force that curves Earth's otherwise straight line motion into an elliptical orbit. Without that gravitational pull, without the Sun's mass warping space-time in its vicinity, Earth would fly off into interstellar space in an absolutely straight line, following Newton's first law perfectly, leaving the solar system behind forever and becoming a rogue planet wandering the galaxy alone, slowly freezing as it moved farther from any star's warmth. But with gravity present, with the Sun's tremendous mass 1,000,000 times greater than Earth's, creating a gravitational field that extends across the solar system, Earth falls toward the Sun continuously, while simultaneously moving forward tangentially. Those two motions, that inward fall and that forward velocity, combine geometrically, like two perpendicular vectors adding together, to create an orbit that curves around the Sun rather than crashing into it. It is, in a very real and precise sense, perpetual falling. Earth is falling toward the Sun right now at this moment, has been falling continuously for billions of years, but because it also moves sideways so quickly, it misses the Sun over and over again. The Sun curves away beneath Earth's trajectory at exactly the same rate that gravity pulls Earth downward, creating a stable orbit that repeats endlessly with astonishing precision. You can visualize this by imagining a thought experiment that Newton himself described. Picture throwing a ball horizontally from the top of a very tall mountain, so tall it rises above the atmosphere into the vacuum of space. The ball moves forward because of your throw, following a straight line tangentially, but gravity also pulls it downward simultaneously, causing its path to curve toward Earth's surface. The faster you throw the ball, the farther it travels before hitting the ground, because it covers more horizontal distance before gravity pulls it down. Now imagine throwing it faster still, so fast that the curvature of its falling path matches exactly the curvature of Earth's surface below it. The ball keeps falling toward the ground because gravity continues pulling it downward, but the ground keeps curving away at the same rate, falling away beneath the ball so that the two curvatures balance perfectly. The ball never gets closer to the surface, it never hits the ground, it just keeps falling in a circle that exactly matches Earth's curvature, orbiting endlessly at constant altitude. That is an orbit, nothing more complicated than falling while moving sideways fast enough that you continually miss the thing you are falling toward. Earth does exactly this around the Sun, except its orbit is not a circle but an ellipse, because its velocity is not perfectly matched to circular motion at all points along the path. At perihelion, when we move fastest, our velocity slightly exceeds what would be needed for a circular orbit at that distance, so we swing outward. At aphelion, when we move slowest, our velocity falls short of what a circular orbit would require at that distance, so we swing inward again. The result is an ellipse, that slightly stretched circle with the Sun at one focus, that we traverse over and over every 365.242 days with remarkable consistency. This orbital motion is described precisely by Newton's law of universal gravitation, which states that every mass attracts every other mass with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. That law, combined with his 3 laws of motion, provides complete mathematical prediction of planetary orbits with extraordinary accuracy. Centuries later, Einstein refined Newton's theory with general relativity, revealing that gravity is not actually a force in the traditional sense, but rather a curvature of space-time itself caused by mass and energy. Massive objects like the Sun warp the fabric of 4-dimensional space-time around them, creating what we perceive as a gravitational field. Earth moves through that warped space-time following what is called a geodesic, the straightest possible path through curved space, which appears to us as an elliptical orbit because the space itself is curved. From Earth's perspective, moving along its geodesic through curved space-time, there is no force at all. Earth is in freefall, just as astronauts orbiting in the International Space Station are in freefall, experiencing weightlessness despite Earth's gravity because they and everything around them are following the same geodesic through space-time. They feel no force, no acceleration, because they are not being pushed or pulled in their own reference frame. They are simply following the natural curvature of space. This is why orbit is sometimes poetically called perpetual free fall. Earth has been falling toward the Sun for billions of years, but moving fast enough sideways that it never gets closer, never collides, just traces out that elliptical path endlessly through the void. The only reason the ellipse is not a perfect circle is because Earth's velocity vector is not exactly perpendicular to the line connecting Earth and Sun at all times, and because the magnitude of that velocity is not perfectly tuned to produce circular motion. At perihelion in early January, we move slightly too fast relative to our distance from the Sun, exceeding the velocity needed for a circular orbit at that radius. This excess velocity carries us outward against gravity's pull, like a ball thrown upward fighting against Earth's gravity, gradually slowing as we trade kinetic energy for gravitational potential energy. At aphelion in early July, we move slightly too slow for our distance, moving slower than a circular orbit would require at that radius. Gravity pulls us inward again, accelerating us, trading potential energy back into kinetic energy as we fall toward the Sun. The balance between kinetic and potential energy remains constant over the orbit if we ignore tiny perturbations from other planets. This is conservation of energy in action, one of the most fundamental principles in all of physics. Energy cannot be created or destroyed, only transformed from one form to another. As Earth swings outward from perihelion, kinetic energy decreases, while potential energy increases by exactly the same amount. As it swings inward toward perihelion again, potential energy decreases while kinetic energy increases, maintaining perfect balance. The total orbital energy remains constant, and that constant energy determines the size and shape of the ellipse forever, or at least until some external force adds or removes energy from the system. NASA and other space agencies use these same principles, these same fundamental laws of physics, to design spacecraft orbits with extraordinary precision. Every satellite around Earth, every probe sent to Mars or Jupiter or Saturn, every flyby of Venus or Mercury follows the same physics Newton and Einstein described. Engineers calculate the exact velocity needed for a given orbit at a given altitude, launch the spacecraft to that speed using rockets, and then simply let it coast. No fuel is burned to stay in orbit once the spacecraft reaches its destination. The spacecraft just follows its geodesic through space-time, tracing an ellipse or circle, or more complex path depending on its exact velocity and position when the engines shut off. Only small corrections are needed occasionally to counteract minor perturbations from other gravitational sources like moons or planets or the Sun's irregular mass distribution, or to adjust the orbit for specific mission requirements. But the basic orbital motion is free, requiring no energy expenditure. In fact, one of the most beautiful and elegant things about orbital mechanics is precisely this energetic efficiency. Once you are in orbit, whether around Earth or around the Sun or around any celestial body, you can stay there essentially forever without expending energy, assuming you have reached a region where atmospheric drag and other dissipative forces are negligible. The International Space Station has orbited Earth continuously for more than 2 decades, its crew changing regularly, but the station itself enduring in its orbital dance. It requires periodic boosts from attached spacecraft to counteract the thin wisps of atmosphere that still exist at its altitude of about 400 kilometers, creating tiny but cumulative drag that slowly circulates orbital energy into heat, but these boosts are small and infrequent. If the station orbited just a bit higher, where the atmosphere is even thinner, perhaps at 600 or 1,000 kilometers, it could remain aloft for centuries with no intervention whatsoever, following its orbit perfectly through the near vacuum of near-Earth space until the orbit naturally decayed after thousands of years, or until some catastrophic event like a major collision destroyed it. Earth itself orbits in nearly perfect vacuum. The space between planets is not completely empty, as I mentioned. There are scattered hydrogen atoms left over from the formation of the solar system. There are dust grains, tiny fragments of asteroids and comets that broke apart over millions of years. There were occasional asteroids large enough to perturb Earth's orbit infinitesimally if they pass close by. But the density is so extraordinarily low, the vacuum so nearly perfect, that the drag force and energy dissipation are utterly, completely negligible. NASA estimates that if no other forces acted on Earth, if we could somehow remove or ignore the gravitational perturbations from other planets and the Moon, if we considered only Earth and the Sun in isolation, Earth's orbit would remain stable for billions of years at minimum, essentially until the Sun itself evolves off the main sequence and becomes a red giant star in about 5 billion years, swelling enormously and engulfing the inner planets. But other forces and effects do exist in reality. The gravity of other planets, particularly Jupiter, with its immense mass of more than 300 times Earth's mass, tugs gently on Earth as the giant planet orbits the Sun. These perturbations are tiny compared to the Sun's gravitational dominance, measured in parts per billion or trillion of Earth's orbital motion, but they accumulate over very long periods, causing subtle changes in the orbit's shape and orientation. Venus and Mars, Earth's nearest planetary neighbours, also exert small gravitational forces that perturb the orbit slightly. Even the Moon, despite being much smaller than Earth, has gravitational effects because of its proximity. Astronomers account for all these effects using complex mathematical models that treat the solar system as an n-body problem, with n equal to the number of significant masses, each planet and large moon influencing every other through gravity's infinite reach, creating a web of forces and motions that must be solved numerically using powerful computers. These models show something fascinating and slightly unsettling. Earth's orbit is chaotic over extremely long timescales, on the order of tens or hundreds of millions of years. This does not mean the orbit is unstable, or that Earth will crash into Venus or fly off into space. The term chaos in physics has a precise technical meaning. It means that tiny differences in initial conditions, differences too small to measure with any instrument, amplify exponentially over time until the exact position and velocity become unpredictable beyond a certain time horizon. For Earth, that horizon is somewhere around 50 to 100 million years depending on what precision you require. Beyond that point, the accumulated tiny uncertainties in our measurements of current positions and velocities, uncertainties of mere centimeters or millimeters, amplify through the complex interactions with other planets until we cannot predict Earth's precise position in its orbit anymore. The orbit might be slightly more elliptical or circular. Perihelion might occur a few days earlier or later. The orbital plane might tilt by a fraction of a degree. These changes are small, probably too small to significantly affect climate or life, but they demonstrate the profound sensitivity of complex dynamical systems to initial conditions. This sensitivity is sometimes called the butterfly effect, after the poetic notion that a butterfly flapping its wings in Brazil could eventually cause a tornado in Texas through cascading effects in the atmosphere. Similarly, a single large asteroid strike or a close passage of a rogue star through the outer solar system millions of years ago could have shifted Earth's orbit infinitesimally at that moment, but that tiny shift compounds over millions of orbital periods until it produces measurable differences in orbital parameters today. However, despite this mathematical chaos, the orbit itself remains stable in the sense that matters for life. Earth will not suddenly fly off into space. It will not plunge into the Sun. It will not collide with Venus or Mars. The chaos manifests in the precise position and timing, not in the overall structure or stability of the orbit itself. The solar system has existed for 4.5 billion years without Earth straying from its general path within the habitable zone around the Sun, and simulations suggest it will continue that way for billions more, at least until external factors like the Sun's evolution change the system fundamentally. This stability is, once again, part of what makes complex life possible on Earth over geological timescales. If Earth's orbit changed dramatically, shifting the planet's average distance from the Sun by even just a few million kilometers over thousands or millions of years, the climate would undergo such severe shifts that evolution could not keep pace. Species would go extinct faster than new ones could adapt and emerge. Closer to the Sun by just 5%, about 7 million kilometers, and average temperatures would rise dramatically. Oceans would begin to evaporate more rapidly. A runaway greenhouse effect, like the one that turned Venus into a hellish inferno, might initiate, boiling the oceans away entirely and leaving behind a dead, scorched world. Farther from the Sun by a similar margin, and temperatures would plunge. Ice sheets would advance from the poles toward the equator, reflecting more sunlight back into space and causing further cooling in a runaway process. Eventually, the entire planet might freeze solid in a snowball Earth scenario that has possibly occurred several times in Earth's distant past, but from which the planet recovered through volcanic emissions of greenhouse gases and other mechanisms. Today, life clings to a narrow zone of stable conditions that depends critically on Earth maintaining its current orbital parameters. Remarkably, Earth has remained within that narrow habitable zone, that band of orbital distances where temperatures allow liquid water to exist on the surface, for billions of years despite the Sun gradually changing its properties. When life first appeared on Earth about 3.5 billion years ago, single-celled organisms in ancient oceans, the Sun was about 30% dimmer than it is today, less massive through loss of material, younger and cooler in its core where fusion occurs. Yet somehow, the planet did not freeze into a permanent ice world despite receiving far less solar energy. Instead, the atmosphere adjusted naturally over millions of years, possibly containing much higher concentrations of greenhouse gases like carbon dioxide and methane that trapped heat more efficiently and compensated for the weaker sunlight. Volcanic activity released these gases continuously. Early life forms modified the atmosphere through their metabolism. The system found a balance, creating what is known as the faint young sun paradox in planetary science. The Sun was faint, but Earth remained warm enough for liquid water and life, highlighting how complex and interconnected Earth's climate and geological systems truly are. As the Sun has brightened over billions of years through natural stellar evolution, gradually growing more luminous as helium ash accumulates in its core and changes the fusion dynamics, the atmosphere has compensated by reducing greenhouse gas concentrations through various natural processes. Plants and algae remove carbon dioxide. Weathering of rocks consumes it slowly over geological time. The ocean absorbs it. The system maintains equilibrium through negative feedback loops that have kept Earth habitable across enormous spans of time, even as the Sun's output steadily increased. But this balancing act cannot continue forever. As the Sun continues to age and brighten along its evolutionary track, Earth will eventually, inevitably, move out of the habitable zone, not by changing its orbit, but by the Sun changing its nature. In about 1 to 2 billion years, the Sun's increasing luminosity will make Earth too hot for liquid water to exist anywhere on the surface, even with reduced greenhouse gases. The oceans will slowly evaporate into the atmosphere. Water vapor, itself a powerful greenhouse gas, will trap even more heat in a runaway process. Eventually, ultraviolet light from the Sun will break apart water molecules in the upper atmosphere, and hydrogen will escape into space while oxygen reacts with surface rocks. Earth will lose its oceans permanently, becoming a desiccated world like Venus is today. Long before that final desiccation, perhaps within 500 million to a billion years, life will face tremendous challenges as temperatures rise and water becomes scarce. Complex multicellular life, especially large animals that require consistent water and moderate temperatures, will struggle to survive. Perhaps life will retreat to deep ocean vents or underground aquifers or polar refuges, clinging to existence in ever-shrinking habitats. Perhaps new forms of life adapted to hotter conditions will evolve. Perhaps intelligence will develop again in species that emerge after humans are long gone, and those beings will find technological solutions to the problem, building shields in space or modifying the atmosphere or even moving Earth to a safer orbit using gravitational tugboats or other megascale engineering we cannot yet imagine. But these timescales are so vast, measured in billions or hundreds of millions of years, that they are almost meaningless to our immediate experience or to our civilization or even to our species as currently constituted. For now, and for countless generations to come, for periods of time longer than all of human history multiplied 1,000-fold, Earth's orbit will remain stable and comfortable, carrying us around the Sun year after year in that same precise elliptical path, neither growing nor shrinking significantly, maintaining the conditions that allow life to flourish. And so, returning to the original question that opened this section: what keeps Earth moving around the Sun? What maintains this motion year after year, epoch after epoch? The answer is elegant in its simplicity: inertia, momentum. The straightforward fact that once set in motion in the near vacuum of space, an object continues moving until something stops it. And nothing in the solar system, no force available to physics as we understand it, is powerful enough to stop Earth, not even close. Not by orders of magnitude. Earth will orbit the Sun until the Sun itself dies, until our star exhausts its hydrogen fuel and swells into a red giant, expanding its outer layers to perhaps beyond Earth's current orbit, possibly engulfing our planet entirely in a thin ionized plasma that was once the Sun's surface, dragging Earth inward through friction until it spirals into the stellar core and vaporizes. Only then, consumed by the very star it once orbited faithfully for billions of years, will Earth's motion finally cease. Until that distant, almost unimaginable future event 5 billion years hence, we ride through space aboard this ancient world, this spacecraft we were born upon, tracing our ellipse year after year without effort or fuel or propulsion, held in orbit by gravity, carried forward by momentum, requiring absolutely nothing at all to maintain this cosmic dance. It is a sobering and beautiful thought. The ground beneath your feet is moving at 108,000 kilometers per hour right now, and it will continue that motion effortlessly, gracefully, long after you and everyone you know, and every human who lives today has become dust scattered across this world, eventually recycled into new life or new rock or new water in the endless cycles of geology and biology that continue regardless of individual existence. But while Earth's orbit remains remarkably stable over human timescales and even over millions of years, other aspects of its motion and our measurement of that motion are not quite so stable or simple. There is another rhythm, another layer of complexity in how we track Earth's movement and count the passage of time, something even slower and more subtle than the seasons, more gradual than the equation of time we explored earlier. A discrepancy so slow you would never notice it in a human lifetime, or even in 10 lifetimes, but so powerful and so significant that it has reshaped human civilization's entire understanding of time itself. As this quiet journey comes to an end, I hope these moments among stars and science brought you a bit of calm tonight. Every tick of every clock, every sunrise and sunset is part of Earth's steady motion through space, a rhythm that has carried life for billions of years. If this story helped you drift a little closer to rest, a gentle like or subscribe truly helps me continue creating these peaceful voyages through the universe. And if you'd like, you can share where you're listening from. Your comments are like small lights across the darkness. They guide the next journey. Now let the Earth carry you through the night. Even as you rest, you are traveling thousands of kilometers every hour, orbiting the Sun, moving with our galaxy through the vastness of space, yet it feels still, safe and quiet. Sleep well, traveler of the cosmos. You are part of this universe, made of its atoms, shaped by its motion, connected to every star. When you wake, the Sun will be waiting, not because it rises, but because the Earth turns you gently back into the light. Good night, fellow passenger on Spaceship Earth. Rest deeply. Morning will come again, and the dance continues.